Geestra, an international manufacturer of valves and control technology, commissioned the world's first complete glass steam system in 2009. For the first time ever, it's now possible to look right into a steam generator and see how steam bubbles arise, how feed water is deaerated, and how the various types of steam traps really work. A number of videos take a look at important facets of the steam condensate system and its operation, thermodynamic processes taking place in the generation of steam, as well as during condensation, condensate discharge, and the origination of the water hammer effect are shown in a way that's easy to understand. This video looks at condensate discharge using various kinds of steam traps, as demonstrated in the glass steam system of Geestra AG, Bremen. The steam system consists of a secondary steam generator with a service pressure of 1.3 bar G, corresponding to a saturation temperature of 124.7 degrees centigrade. The capacity of the steam boiler is 50 kilowatts, which yields a steam flow rate of 80 kilograms per hour. As the condenser, we're using a glass heat exchanger mounted above the steam generator. The cooling water flows in the tubes, while the steam flows in the jacket around the tubes. After passing through the steam traps, the condensate is collected in a glass condensate tank at normal atmospheric pressure. By looking into the heat exchanger, we can see the condensation on the individual glass tubes, through which the cooling water flows from right to left. The drops that form soon fall off the tubes, collect at the bottom of the heat exchanger and flow towards the outlet. The steam traps used for draining the heat exchanger are mounted below the heat exchanger. This video presents the ball float trap, type UNA16. The flow trap is preceded by a special sight glass, the Vaporscope VK16. This is used for monitoring the steam traps and making the flow processes visible. A deflector inside the Vaporscope sight glass forces the condensate to flow through a small siphon. A small steam space is formed in front of the deflector, and the deflector is slightly immersed in the condensate. The following steam trap is used for discharging only condensate. Steam does not pass below the deflector. Now the flow trap is opened with the aid of its float lifting lever, so that steam is forced to flow through the steam trap. The deflector immediately emerges from the water, since the steam passing through now presses the condensate downwards into the siphon. This is a clear indication that the steam trap is causing loss of steam. Here the Vaporscope is completely filled with condensate, which points to a banking up of condensate in the trap. Geestra ball flow traps have a regulator which functions by having a float pull a rolling ball off an orifice when condensate flows into the body. This opening is called the orifice and can have various diameters depending on the differential pressure. Through the differential pressure that is applied, the condensate is pressed through this small orifice and flows through the condensate line into the vessel located downstream. At the start of every heating process, there is still air in the heat exchanger. Air or other non-condensable gases must be vented from the heating process by the steam traps, since they will greatly impair the exchange of heat. For this reason, the Geestra ball flow trap has an additional thermostatic control to handle this task. With the UNA16, this is a small regulating membrane which, through the temperature difference between saturated steam and air, detects whether there are any unwanted gases in the heating system that would impair the heating process. As an optional arrangement, a float lifting lever is mounted on the flow trap. This offers the possibility of achieving a forced opening of the unit. This may be necessary in practice whenever dirt increasingly accumulates in the steam traps as a result of increased corrosion in the system. In comparison to thermostatic steam traps, ball float traps offer special benefits. Even at very low differential pressures, ball flow traps are able to discharge large quantities of condensate. If the steam trap is sized correctly, the heat exchanger will always be drained without any banking up. This in turn will ensure that the product is always heated correctly. If the steam is controlled and the steam pressure varies as a result, this will have hardly any influence on the condensate discharge, which will still be controlled solely by the level in the trap, independently of pressure and temperature. Owing to the large volume offered by the body of a ball flow trap, fluctuations in flow rate can be handled easily. The steam trap is not prone to hiccups. Because the flow velocities are low, particles of dirt can precipitate at the bottom of the body and will therefore not influence the seat tightness at the orifice. Ball flow traps operate continuously. Because the float ball always floats on the condensate, moving up and down only slightly, the wear and tear is minimal, and the service lifetime of flow traps is often 2 to 5 times as long as that of thermostatic steam traps. With this arrangement, the float trap is installed correctly. It's located below the heat exchanger. The condensate can flow vertically downwards through gravity. Steam bubbles can rise up freely and return to the heat exchanger. The nominal size of the condensate line should not be chosen too small, so that the calculated flow velocity of 0.5 meters per second is not exceeded. Built-in strainers should be cleaned at regular intervals to prevent an unwanted pressure loss. Even if the amount of condensate varies or the operating pressure is changed, the flow trap is able to discharge the condensate over a large control range without any banking up. To demonstrate this, the operating pressure is now reduced to 0.5 bar G with a constant flow of cooling water. For certain installations, it's advisable to provide a non-return valve downstream of the flow trap. If it's possible that the back pressure is higher than the upstream pressure, this prevents a reflux of condensate. When the steam control valve at the input of the heat exchanger closes, this can result in an extremely rapid pressure drop. A vacuum may be produced inside the heat exchanger. Condensate is then drawn through the steam trap back into the heat exchanger. This too is prevented by a non-return valve. In both of these cases, the Gestra Disco non-return valve type RK has proven to be most effective. Just how rapidly the pressure in a heat exchanger can drop will now be demonstrated by closing the ball at the steam inlet of the heat exchanger. By washing the pressure gauge at the same time, we can see how the pressure drop occurs. When the operating pressure is increased again to 1.3 bar G, the flow trap drains the heat exchanger immediately without banking up. It's absolutely essential to ensure drainage without any banking up for horizontal heat exchangers. An accumulation of condensate in the heat exchanger leads to the dangerous water hammer effect, floods the heating surface and reduces the heat transfer coefficient by a factor of about 4. As a result, it's no longer possible to guarantee that the product passing through the heat exchanger is adequately heated at all times. It's recommended that thermostatic steam traps not be used in the case of large heat exchangers controlled on the steam side. Thank you for watching.